To begin section 7.1, we're going to start with discussing taking samples for sample means and averages. And so we're going to do proportions as well, but for here, we're just going to start with the averages since we kind of did that in the previous video. And so if we focus on the shape and center and spread, and so we're going to focus on these areas for this chapter. So the first thing we want to talk about is a sampling distribution. So the sampling distribution of a statistic is a probability distribution for all possible values. So when we do probability distributions for a statistics, it's a sampling distribution. The sampling distribution of a sample mean is a probability distribution for statistics about the mean, right? So it comes from us. It's again the sample size is size n. We have a population mean that we're essentially estimating and the standard deviation. Because remember, we're going to take the averages of what the average is. So because this isn't exactly from the population, and we saw from all the Reese's Pieces samples and the Excel spreadsheet of like the little set of odd numbers that the population mean, you know, remember if I took the average of the averages, that was the population average and the standard deviation, right? So we cannot just say mu because that's just the population mean. So we have to say, hey, this is the population mean that we estimated from a sampling distribution. And so that's why we put a mu sub x. So notice that it's mu and then the sub x for the random variable. So mu sub x says this is the population's mean that we estimated from a sampling distribution. So likewise with the sigma, remember that sigma sub x is the population standard deviation, but it isn't the population standard deviation. We estimated it by the sampling distribution, right? So this sigma sub x would be, say that we estimated the standard deviation from a sampling distribution. And essentially because we're assuming we're taking so many samples and taking larger and larger sample sizes that these actually end up being the same as the population. But we just go ahead and put the sub x as a random variable to demonstrate to the reader that we're doing it from a sampling distribution. That's all. And so the box below just puts it, you know, the way the book has it as the distribution. So now notice that this x bar, so the average of the averages, is a normal distribution such that mu sub x, right? So the mean with respect to the sampling distribution, comma, and then this whole thing replaces the population standard deviation that we had in chapter 6, right? Or chapter 5. So 6 and 5. And so now because we're taking so many samples, right? We're taking so many samples, right? We're taking more and more samples that this is ever, you know, it's ever changing per sample. So this is just stating that the standard deviation with respect to the sampling distribution, which would be sigma, has to be divided by the square root of n, by the sample size. And why? And that's just because we're taking it, this is just because we're taking it from a sampling distribution. That's all. And it's ever changing, and we saw that with, they changed a little bit, but not too much. So this is called something, because we really can't call it the standard deviation, you know, with respect to the random variable. It seems like a lot. It's actually something special because it's so common in statistics. And so we do call this the standard error. And essentially all you're doing is, if you're given samples and you're finding the average of the averages, you're always going to divide by the square root of n. It's just going to be a habit. And so even if you are given one sample, you're going to divide by 1, right? If you're given 20 samples, then you're going to divide by the square root of 20. So let's try an example. So suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. Write the distribution, like in the box above. So Okay, so here we know that the average time for a 10-minute oil change, according to the distribution, is 11.4, and the standard deviation with respect to the sampling distribution is going to be the 3.2, but then divided by a sample size, which we don't know yet. So we would have x bar tilde normal distribution parenthesis 11.4 comma 3.2 and then divided by the square root of n. The next example says if a random sample of 35 oil changes is selected, describe the sampling distribution of the sample mean. So when we want to describe the sampling distribution, let me underline this. Okay, this means we're going to describe mu sub x and sigma sub x. Okay, bar, sorry. So this means that mu sub x, remember the mean average of the average stays the averages, but the standard deviation deviates a little bit. So this means that the standard deviation with respect to the random variable will be 3.2 divided by the square root of the sample size 35. Okay, and you don't have to calculate it. We're not going to be doing much with it. The last part of this example says if a random sample of 35 oil changes is selected, what is the probability of the mean oil change is less than 11 minutes? So in this case, notice because we assume normal distribution because of the central limit theorem, that we'll mark the mean as usual as 11.4. And so these tick marks are standard deviations away. So if we went ahead and found those tick marks, we would use this standard deviation. So if I went to the calculator, I would have 11.4 plus 3.2 divided by the square root of n. So that would be the first one to the right. So we'll do 11.9. Hit second and enter and put a times 2. And we'll have 12.5 as the next one. And we'll just do 3, right? So that, and then change that 2 to 3. And we get 13.0. So let's do it to the left. Hit second, enter, and then I'm going to go ahead and just change that to a 1 and then change that plus sign to a minus. So that's the first one to the left, 10.8, 10.9. And then second, enter, change the 1 to a 2, 10.3. And then second, enter, change the 2 to a 3, and so 9.8. So if I want to see the mean oil change time is less than 11 minutes, I'm going to mark that 10.9. It's probably about here. And notice less than 11 minutes means what? To the left or to the right? That's right, to the left. I know you were all thinking it. So here's the mean, here is where 11 is, and we can see that because half of this normal curve is 50%, we know that this probability is going to be less than half. Okay, so how do we do that? Well, it's the same thing. So the first thing we notice that since n is greater than or equal to 30, right? where n is equal to 35, we can assume normality. The second piece we need to note is that our standard deviation with respect to the random variable is 3.2 divided by the square root of 35. Okay, and the third piece is now let's go ahead and answer the question. And we already know that mu sub x bar is the 11.4. So we have all our pieces that we need now. So the probability that a randomly, if I took a random sample of 35 and that mean oil change time is less than 11 minutes, that's going to be equal to normal CDF, right? Left endpoint, which is all the way to the left, so negative 1 E99, comma, all the way up to 11, comma, the mean, which is 11.4, and the standard deviation with respect to the random variable, 3.2 over the square root of n. So you can just put that in the calculator, go to your calculator, hit second vars, go to normal CDF number 2, and the lower is already there for some reason. And then I stopped at 11, and my average was 11.4, and my standard deviation, go ahead and put the exact value, right? The square root of 35. And so here on the calculator, we get 0.2298. 0.2298. And let me go ahead and drag that picture over. Just make it super tiny. I'll put it over here in the corner. And so we can see that it definitely was less than half. And what does this mean? That there is a 0.2298 chance that the mean time is less than 11 minutes.